Hi everyone. Today we are going to talk about how to make GPTs from scratch. And this is a series of videos on where I talk to you about how to actually code up a GPT-2 model from scratch. And this is taken from the LLMs from scratch repository from Sebastian Rashka, which I think is an amazing repository which tells you how to sort of compose every part of a large language models from scratch. And I choose GPT-2 small because, as you can see, I can run this on a CPU sort of Colab notebook without any problems. So in this particular video, the only thing I will discuss is about the multi-headed attention mechanism and how that is implemented. And in subsequent videos, I'm going to talk about sort of how the attention sort of fits into the larger GPT-2 model. But just to give you a sense of what the final version looks like, here we give sort of a prompt to the GPT-2, and then we ask it to output a like the next word predictions, and I prompted like once upon a time there was a land, and it sort of predicted these sort of next few like 30 more tokens for me. GPT-2 of course is not the most advanced model. It far from it. As you can see already, like it's sort of starting to repeat itself after 30 tokens, but it's small enough to run on a CPU. It allows us to sort of learn things from scratch, and it's fairly fast on a CPU, I would say. This is what it looks like when I actually prompt it, which is amazing given that it runs on a Colab notebook, no resources on my own computer. So we'll talk about how to sort of compose this function, but the first and the most important part is about composing multi-headed attention. If you want to know more about what attention is, I have a previous video which I will link to, and this is one of the most amazing resources to learn about what a transformer and what the attention mechanism is. I won't go into like a huge amount of detail on this, but it suffices to say that basically we start with a series of tokens, which are sort of a conversion of these words, individual words, into sort of a series of numbers. So the x1 is some vector, typically of like 5, 1, 2 size, and x2 is a similar vector, and so on. And each of these vectors represent words, and then we pass it through this self-attention block, and we get another set of vectors. And that's what the multi-headed attention does. One important thing to understand is that the Z's are basically a weighted average of values of x's, and that's basically what the attention mechanism does. So the value of it is basically saying how much of it I'm going to use, how much of the animal I'm going to use, and so on. And so, yeah, I'm not going to get into like a huge amount of detail on what attention is. I welcome you to look at my previous video and also at this resource. Let's get down to how to implement the multi-headed attention module. And also, Sebastian has a whole chapter dedicated to it, which sort of walks through it in in a lot of detail as another resource. So the multi-headed attention is, as you can see, it has sort of multiple heads. So the idea is to calculate this Z vector from the queries by multiplying the queries and the keys, and then get a weighted average of the values of all of the embeddings of the tokens. And then the multi-headed attention simply sort of concatenates all of these, like if there are 8 heads, it concatenates the Z values of these 8 heads, and that is the final attention, the final sort of Z that is passed on to the next layer. So with that, let's see how it's implemented. So it says that we need the D in and the D out, which are the input and the output dimensions, and the context length, which is sort of the number of tokens we have, or the maximum number of tokens we can have, and then sort of the dropout, and then the number of heads we have, which maybe is like 8. And then the head dimension is the total, like all of the, where did I go? Sorry, all of the C's here. And then this must be divisible by the total number of heads. And that would give us the head dimension. So in this case, the head dimension is like 3. And then this is like 3 multiplied by 8, like 24. Like that would be the D out in this case. So for each of these tokens, we would produce sort of a 24-dimensional vector in this sort of illustrative example. But of course, this is a much larger number in the actual GPT-2 model. So then what happens here is that we calculate this head dimension, and then we want to get the W query key and the value. And let's go back here and see. So the matrix calculation basically says that we want to get the query key and the value for each of these tokens. And the way we get it is by multiplying each of these x's, which are the embeddings, with a matrix with WQ and WK and WV. And these are sort of the learnable parameters of the GPT-2 models, like the values of these matrices. You can convince yourself that this is exactly the same as implementing a linear model. So basically, we'll get sort of, we have 4 input dimensions here, and we multiply it with sort of a matrix with 3 columns. We would get sort of 3 input output dimensions. And so that is exactly the same as using a fully connected linear layer with a like D in equal to 4 and D out equal to 3, for example. And then you can add a bias term if you want. So that is what this says, is that these are sort of learnable parameters which correspond to sort of these matrices. So that's the key, query, and the value. And then there is sort of a final output layer which sort of combines the head inputs. And this is just another linear layer which takes sort of D out number of values and outputs the same D out number of values, but adds some more parameters to sort of tune. And then there is the dropout, and finally there is the mask. Really, like the number of batches is 1 in his case, and the number of tokens is here, like we have 3 tokens. So that's sort of what that means. So that is the shape of the X vector, and what we will largely do in this video is to sort of go through the shapes of these vectors to convince ourselves that we really understand how the attention is implemented. And so now we get the keys, the key, query, and the value by simply sort of multiplying, taking these as the input of the function, and this is a linear layer. So D in, so the X was B num tokens D in, and we will, the linear layer will output B num tokens and D out. Okay. So we go from D in to D out. That makes sense to us. And same here. So maybe can add, same for key and the values. Okay. So, okay. So now we want to do a little bit of a trick, and this is sort of something that it took me a while to get, is we want to get sort of all these multiple heads. So our D out, if you think about like where we had the multiple heads, so our D out is like 24, for example, here, like 8 heads multiplied by 3. So now we want to split it into 8 and 3. So what we do is like keep batch, number of tokens, and then number of heads, which would be 8 in this sort of comic illustration, and then head dimension is 3. So we split 24 into 8 and 3, and that is how we sort of reshape this vector. So that allows us to work on each of these heads separately, and then we would sort of combine the values that we, or concatenate the values that we get from each of these heads. And we do this to every sort of, to both keys, queries, and values. And then we transpose the first and the second. So here we had B, batch, number of tokens, num heads, and dim. And then we transpose like number 1 and 2, like indexes 1 and 2. So we get num heads here and num tokens here. And we do that to like all of them, key queries values. Now we get to calculate the self attention. Let's see where, so what do we do is like first we transpose like the second and the third index of the key. So from here, so this is what the key looked like. The second and the third index is the num tokens and the head dim num tokens. So we transpose those. So we get number of heads, head dimensions, and number of tokens. And let's see. And this is a dot product for each of these heads. And so the query is B number of heads, num tokens, and head dim. And so when we do this matrix multiplication, so B and the number of heads are the same because, you know, and then we multiply a matrix which has num tokens, head dim with head dim num token. So just from like the laws of matrix multiplication, we get num token multiplied by num token, right? So just to be clear, the attention scores are basically this matrix here. So for each, so we have, this is the number of like the number of rows and the number of columns here and the number of tokens. So for each token, we are saying what is the weight we want to give to each of the values for the other tokens, right? So it's clearly like number of tokens by number of tokens, and then we have like the batch, and like for now we can sort of ignore the batch, and then we have for number of heads. So for each head, we calculate sort of this square matrix. That's what is going on here. And then we apply our mask boolean. We sort of we take a huge like number of contexts by context by context. That's the size, and we take like the number of tokens to number of tokens part of it, because we may have less tokens than the context. So for example, like here we have like only a very few number of tokens, whereas like the context size is much larger here. Maybe 1024. Yeah, context length is 1024, but here we probably have like, I don't know how many, but like 1, 2, 3, 4, 5, 6, 7, 8 maybe tokens. So this is what this line does, is to sort of convert it into, like it was a 1024 by 1024 matrix. It sort of converts it into 8 by 8 matrix, and then it sort of does this mask fill. And the reason it uses minus infinity is because we're going to do a soft max, which is going to change the minus infinity to 0, so e to the power minus infinity. So we end up with this matrix after doing the masked fill. So this is where we are. And then, so remember, our size doesn't change. We're still here, B number of heads, num token by num token. And then here we do the soft max. So these minus infinities become zeros, and then the other sort of ones become sort of numbers between 0 and 1. And now we apply a dropout. And okay, so now we have to do some playing around with the yeah, okay. So let's understand what is happening here. So we've got these weights. We want to multiply these weights with the values. So the attention weights have the shape of num heads. Like, let's ignore the first two. It has like num token multiplied by num token. And the values, like ignore first two, has like num tokens by head dim, right? So we matrix multiplication, the first two things just remain the same. So we get num tokens multiplied by head dim, right? What that means is that for each head, we get like number of tokens size. And then we sort of transpose like index 1 and 2. So we get num token, num heads, head dim. So we transpose index 1 and 1 and 2, num heads and num token. Okay. So that's where we are. Okay. Okay. So now we have to convert it back to this whole like huge concatenated sort of attention head. So we've got each of these ones. So num heads is like 8 and head dim is 3 in this cartoon example. And for each we have sort of num token size vector. And then we just take like, we just reshape it back to num token. So keep the b as the same as the number of tokens and number of heads and head dim, right? Which means that for each of these, so we'll get like num token size vectors of size 24. The reason is this. So let's go back here. Yeah. So we get, so if you think about this example here, so after we pass through the self-attention layer, we're going to get a vector of z1 of size which has a like this whole this huge vector is of size num tokens, right? So if we combine z1, z2 and z3, that is of size num tokens, which is what this num token stands for. And then we multiply by the number of heads and the head dimension, right? So the head dimension is this one, for example, 4 here. So, and then we'll have not just 4, but we'll have 4 multiplied by how many ever sort of heads we have, because for each head we would produce a token. And that is the multiplication here. So that totally makes sense. And we end up with this context vector, which we resize. It has sort of number of tokens and self.dout. Okay. And then, and basically that means that like this is dout. If at the end of the day, this is sort of dout, and like we just combine for all the tokens. Okay, sorry. So num tokens dout, and this is what we forward from the multi-headed self-attention layer. So the multi-headed attention layer. So the multi-headed attention layer, we clearly understand how the forward function works, and basically this illustrates where we take these x's and we get these c's that we then pass to the feed forward layer, and then we will sort of go through what happens after that in a next video, because this is already too long. Thank you for listening to this long video, and let me know if you have any questions down in the comments, and I'll do my best to explain how GPT models work from scratch in this series of videos. Thank you.